So we have two semicircles over here, a bigger semicircle with diameter 2 and a smaller semicircle with diameter 1. And the smaller semicircle is behind the bigger semicircle such that this crescent shape is visible only. And we want to find the area of this crescent shape of the smaller semicircle. So how do we go about this? Well, one way we can go about this is by taking the area of this entire small semicircle and then subtracting off this part right here, because this part is already behind the bigger semicircle, so its area isn't taken into account. So let's write that down. So we have our smaller semicircle, and we want to subtract off this area right here, this kind of sliver that gets covered up by the bigger semicircle, and that will give us our crescent shape that we want. And note that these drawings are not to scale. So if we find the two areas over here and subtract this one from this one, we will get our desired answer. So let's try to find the area of just a normal semicircle. Now how do we do that? Well, the area of a circle is pi r squared, r being the radius. And so for a semicircle, that's half a circle, so we just divide whatever we get by 2. Now what's the radius for the smaller semicircle? It's not 1 because 1 is actually the diameter. The radius is the diameter divided by 2, so the radius is 1/2. So it'll be pi times 1/2 squared divided by 2, and that will give us, after some arithmetic, pi over 8. So now we have the area of the entire semicircle for this right here, but that's not what we want. We want to still subtract this part from the semicircle. We want to find the area here, this area. And how do we do that? Well, now we have to relate the two semicircles together in a way that will give us this area. Now, let's actually use the same approach as we did over here. How do we find this small area right here? That would kind of be difficult to find it on itself. But what if we can take a bigger area and then subtract the area from that figure that we don't want to get this desired area, which is the same thing we did here? Well, let's try that. If we say that the center of the big semicircle is right here, then we can connect this center with these 2 points. And the reason why I'm connecting these 2 points is, well, remember that a radius is just taking a point on any circle and then connecting it to the center of the circle. Well, this is the center of the circle if this semicircle was a circle. So both of these lengths right here is the radius of the circle, this radius of the semicircle. And the diameter of the semicircle is 2, so that means the radius will be 1. So both of these lengths are equal to 1. But we just came across a pretty crazy realization. This side length is 1, this side length is 1, and then this side length is 1 as well. That makes this an equilateral triangle right here. And one thing we know about equilateral triangles is that all of their angles are 60 degrees. So how does this help us? I mean, this is some pretty important information, but will it get us anywhere to the answer? Well, remember, we want to find this area right here. How can we do that? Well, if we take this entire area right here, the area that I'm outlining right now, and then subtract this equilateral triangle area, we will get this area. Let me draw that out. If we take the area of this kind of ice cream cone-like figure and then subtract the equilateral triangle part, we will get, this is just an equal sign, this top part, kind of the ice cream part. You can do this as the cone, this is the ice cream. Subtracting the cone part from the ice cream cone just gives us the ice cream. So now we just have to find these two areas. So how do we find this area right here? Well, recall that you can find the area of any sector of a circle, in this case a semicircle, by just knowing what this angle theta is. Theta is in this case just a variable. Well, we know what this theta is. It's 60 degrees. But what does this 60 degrees tell us? How do we use that to find the area of this sector? Well, recall that a circle has 360 degrees in total. So this is 60 degrees right here. If we take 60 and divide it by the full 360 degrees, we get 1/6. And this 1/6 basically means that this sector right here, this ice cream cone, is 1/6 of the whole area of this circle. In this case, it's a semicircle, but we are pretending that this extends to a full circle. So if we find the area of this full circle right here, and then multiply it by 1/6, we will get the area of this sector. So let's find the area. The area of a circle is pi r squared, as we said before. If the diameter is 2, the radius is 1. So the area of this full circle, if there was a full circle, is pi times 1 squared, or pi times 1, or pi. And then we multiply that by 1/6 to get pi over 6. And pi over 6 is this area right here again. This ice cream cone-like figure. It's basically 1/6 of the total area of the circle. But we want to subtract the equilateral part. We don't want this part, right? We just want this ice cream part of the ice cream cone. So if we subtract the cone part, we basically have to subtract the area of this equilateral triangle. And as you may recall, the area of an equilateral triangle is square root of 3 divided by 4 times the side length squared. In this case, the side length is just 1, so times 1 squared, or times 1, which will just give you square root of 3 over 4. So we have our ice cream cone area. We subtract the cone part. So this area right here is equal to pi over 6 minus the square root of 3 over 4. However, we are not done yet. We want to find this crescent area right here, not this area. We do have this area, which is important, because now we can subtract this area from, as we drew in our diagram, this area, the area of the smaller semicircle. This entire thing right here. So we take this, subtract it from the area of the semicircle, the smaller semicircle, which was pi over 8, and we're at the end game now. We have pi over 8 minus, what was it? Pi over 6 minus the square root of 3 over 4. Okay, let's multiply the numerator and denominator by a certain amount. Let's multiply by 4. By 3, we get 3 pi over 24. And the reason I multiply like that is because if you multiply pi and 6, the numerator and denominator, by 4, you get minus, and if we take this minus sign and expand it to the terms, we get minus 4 pi over 24. And then this minus and this minus becomes a plus square root of 3 over 4. And now we have 3 pi over 24 minus 4 pi over 24. And let me just write this first. We have square root of 3 over 4 minus pi over 24. So the square root of 3 over 4 minus pi over 24 is our desired area, which is this crescent-like figure. And we are done.